Hello everyone, so in this lecture video we're going to be talking about colligative properties, okay? And colligative properties are properties of solutions, okay, based on the amount of substance that's dissolved in it. So in this case we're talking about a pure substance. In this case we're talking about the pure substance water and the effects of dissolving something in water. And the three main colligative properties that we're going to be talking about in this class is going to be boiling point, freezing point, and osmotic pressure. And all of those three properties can be affected by the amount of substance or solutes that are dissolved in water, and obviously solutes, whether they're liquids or solids, in a water solution are called aqueous solutions. Okay, so a brief review about boiling points and freezing points of water. So the boiling point of water is 100 degrees Celsius, and the reason why this has something to do about the vapor pressure. So here what we have to understand is this is pure water, and any liquid at any temperature will always have molecules that's going to be escaping from the liquid phase to the gas phase, and there's also going to be molecules that's always going to be transitioning from the gas phase to the liquid phase. And this is going to be dependent upon whether the particles in the air and the particles in the liquid are actually, in this case, miscible, or in this case, similar to each other. Okay, so there's always going to be gas particles that actually evaporates, and this is one of the reasons why during a hot day, if you live in a hot, non-humid day, a dry day, if you actually leave in this case, a full glass of water outside, eventually you will notice that some of the water levels are going to be declining, and that's the reason is because of evaporation. Okay, so in this case, this is evaporation. Which is regular. It happens at any temperature. At around room temperature, which is around 25 degrees Celsius, the vapor pressure of water is around 19.8 millimeters of mercury. That is actually how we measure it. We're going to be looking at other measurements of pressure eventually when we talk about gases, but this is which is at the end of the, but this is 19.8 millimeters of mercury. The vapor pressure, the atmospheric pressure, and the atmospheric pressure is the pressure being exerted by the atmosphere. So the atmosphere is also pushing down, and this is actually around 760. So you have two forces. You have 760 millimeters of mercury pushing down, and you have around 19.8 millimeters of mercury pushing the particles from escaping from the solid, from the liquid to gas phase, and right, obviously 760 is going to be pushing them back into the liquid phase. All right, so that's at 25 degrees Celsius. What happens is, in order for water to boil, we know that we need to reach 100 degrees Celsius. And the reason why 100 degrees Celsius is a magical number is at 100 degrees Celsius, we have introduced enough energy, enough heat at the point of 100 degrees Celsius. And at that much heat, what happens is now the vapor pressure of the liquid water, in this case, is going to be way, way, way greater, okay, or equal to, in fact, it's going to be greater, all right, than 760. So again, there's two interactions in play here. The vapor pressure, which is the pressure exerted by the liquid, and the atmospheric pressure, which is the pressure exerted by the atmosphere, whatever is air is outside, right? So the way that water boils is it has to exceed the 760 millimeters of pressure that is actually being exerted by the atmosphere. Think about it this way. If someone is trying to think about atmospheric pressure as someone pushing someone down, all right? So at very low temperatures, and even at room temperature, that person that this atmospheric pressure is pushing down has not enough power. Okay? So what happens, however, is if you heat up the solution, that person that the atmosphere is pushing down, the vapor pressure, is gonna become stronger than the atmospheric pressure, and at that point it can escape into the gas phase. All right, so that's the relationship between pressure, vapor pressure, and temperature. The higher the temperature, the higher the vapor pressure. The lower the temperature, the lower the vapor pressure. And that is why water freezes at extremely low temperatures. Okay, so again, very, very important here. Okay, so what does that have to do with boiling point? Right, so pure water boils at 100 degrees Celsius. If you introduce solutes, especially ionic solids, right, we know for a fact that ionic solids in an aqueous solution splits up into their constituent ions, the sodium ion by itself and the chloride ion by itself. And what they do is this positively charged sodium ion is going to interact with the oxygen, right? And remember, there's two hydrogens of a lot of water molecules. And for the chlorine ion, it's going to be the opposite. It's going to be the hydrogen molecules, which are partial positive, that's going to be attracted to the chloride molecules. This is partial positive, right? The oxygen is obviously partial negative. So the partial negative oxygen is going to be attracted to partial, or in this case, the full positive sodium, right? So there's going to be a lot of interactions between sodium and chlorine molecules plus other water molecules, okay? So as you increase the temperature, as we talked about in the previous slides, what happens now is this water molecules, this liquid water molecules, right, are going to transition into the gas phase, right? So a pure solvent, pure water, boils at 100 degrees Celsius. However, when you have ionic solids like sodium chloride dissolved in water, there are two things that prevents the water molecule from escaping to the gas phase. One of them is the obvious interaction between sodium and the water molecules, and not just sodium but chlorine as well. So if you have two ionic particles attracting water molecules, what happens is the sodium and chloride molecules are basically grabbing on to the water molecules and preventing them from escaping to the gas phase. So that is one of the reasons why when you add a salt into water, that solution is going to boil at a higher temperature. I'm just going to make up a number here, 110 degrees Celsius. Okay? So that's one reason why water that has dissolved solids actually boils. In this case, soluble solids boils at a higher temperature. The other thing that happens is there's an interface between the gas phase and the liquid phase, right? So if this is water, there's an interface. Normally, if this area is uniformly water, water is going to be very, very easy to escape from the liquid to gas phase. However, if you introduce ionic solids on that surface, what happens is those ionic solids, sodium and chloride in this case, prevents the aggregation or the collection of water molecules on the surface. Therefore, there are less water molecules on the surface that are able to escape into the gas phase. So those are the two effects on boiling point of soluble solids in water. Now, why does in this case silver hydroxide not affect the boiling point of water? The reason why is silver hydroxide is going to settle on the bottom and it will not interact appreciably with water molecules, or it will not break the interface between the gas and liquid phase, the transition phase in this case. All right, so that is one of the explanations why water that has something soluble in it will boil at a higher temperature. Now, this is the same as well for freezing point. So in order for water to freeze, water has to, in this case, has to aggregate a little bit closer together. Actually, this is actually a misnomer because solid water is actually less dense than liquid water. But just for purposes, if you're a liquid, you're this far apart, and as you become a solid, the distances between these two particles now become closer together, because that's actually and if you're a gas, the particles are very, very far apart from each other, right? So it's everything about the states of matter is about distances between particles, okay? So what happens is, if there are no dissolved solutes in pure water, these two water molecules are going to be very, very easily associated with each other. But similar to the effects of soluble solids to liquid water and its boiling point, what happens is as these two are trying to get together because they're trying to become a solid, now you have sodium pulling on this water molecules, and now you have chlorine on the other end. So therefore, these two water molecules is harder for them to become closer together. So that is one reason why water freezes at a lower temperature when a solute is dissolved in it. The other thing is obvious is the gaps. So if you have sodium in between two water molecules, it prevents this two water molecules into making close contact together, creating a crystal and creating a solid in this case. This is the reason why we throw salt in our driveways during the winter time. Because if you throw salt, all right, normally this freezes at 0 degrees Celsius. Now if you throw salt, now this is no longer true, and now it's gonna freeze at a lower temperature. Okay? So that is actually one of the reasons why we throw salt in our driveways and our streets during the winter time. And actually that's not a very healthy thing for the environment, by the way, but that's a different thing for a different time. All right? This is actually a diagram that shows you the effect of a solute, a miscible liquid, and a soluble solid on the boiling point and the freezing point of a pure substance. So as you can see, there's a leftward shift and there's a downward shift. And so anytime you dissolve something that's soluble or miscible in water, it is always going to decrease the freezing point, and it's always going to increase the boiling point. All right? This is the temperature, right? So as you can see, if it goes down, so again, that is actually the main case in this case. All right? So here you can see that the old boiling point of pure solvent, now it's higher. Here, this is the pure solvent freezing point, and now it's lower. All right? So very, very important key thing here. And again, this was a phase diagram that you have seen before, right? Pressure on this axis and temperature on this axis. So we've talked about freezing point and boiling point. And now the last colligative property we're going to be talking about is osmosis. So we have three types of solution. You have hypotonic, isotonic, and hypertonic solution. And I'm just going to simplify this. Red blood cells, for our purposes, okay, it's much more complicated than this, is around 0.9% sodium chloride. Okay, and I'm just negating all the other ions in this case. So let's just assume that this is all sodium chloride, which is not true, but I'm generalizing here. If it's 0.9% sodium chloride, therefore it has to be 99.1% water. All right? A hypotonic solution is a solution that is a higher, so if I introduce, let's just do an example, all right, 100%, wow, that's a terrible percent, water to a 0.9% sodium chloride red blood cell, which is 99.1% water, there's going to be a net flow of water. So water is going to enter from an area of greater concentration. This is 100% water. This is 99.1% water. So it's going to go from an area of higher concentration to an area of higher concentration. And this is why in a hypotonic solution, hypo meaning lower tonicity, so this means it's 0% sodium chloride, folks, right? Hypo meaning lower, that's higher. This is why water flows in here, and that's why most red blood cells in a hypotonic solution will blow up. In a hypertonic solution, it's the opposite. So if I introduce something that's 10% sodium chloride, which means to say it's 90% water, what happens? What is the movement of water? Water then is going to flow from the red blood cell out. And that is why in hypertonic solutions, it's 10% sodium chloride, 0.9% sodium chloride, the actual red blood cells actually shrink, shrivel up like raisins. This is the reason why we have to inject, especially in the bloodstream, isotonic solutions to patients. Isotonic solutions mean they have the same concentration of salt. So if I inject a similarly 0.9% sodium chloride solution, what happens is since the water concentrations are equal between the solution and the red blood cells, there is no net flow of water. That is called osmosis.